LSM-Trees are the darling of write-heavy systems. RocksDB, Cassandra, LevelDB, they all promise blazing fast writes. But there's a brutal hidden cost. The same design that makes writes so fast inherently wrecks your reads. Today, we're going to dissect exactly why and what you can do about it. The core idea is simple. Instead of updating a tree in place, you just append new data to a log. Later, you merge and sort it in the background. All disk writes are sequential, which is the fastest path on any storage. That's why an LSM tree can ingest 1,000,000 writes per second on a single server. Compared to a B tree, an LSM tree can handle 5 to 10 times the write throughput. Facebook's MyRocks moved from InnoDB to RocksDB for their social graph storage, and cut the storage footprint in half while drastically increasing write speed. But that speed came with a catch, and it shows up the moment you try to read data back. When you write a key, the new value gets appended to a log, but older versions still exist in previously sorted tables. A read now has to hunt through potentially dozens of files to find the most recent version. That's read amplification. For a single key lookup, you might end up doing 10, 20, or even 100 disk reads. Let's walk through the architecture. Writes land in an in-memory memtable, sorted by key. When it fills up, it's flushed to disk as a sorted string table, an SSTable. The first level, level 0, contains these flushed tables, but their key ranges can overlap. Lower levels are formed by compaction. They're sorted, non-overlapping, and each level is typically 10 times larger than the one above. RADs must check the memtable, then level 0 files, then each deeper level until the key is found. Without optimizations, the read code must scan every level 0 file because their key ranges can overlap. For each lower level, it binary searches the right sorted table and probes it. Each Bloom filter probe requires a disk read, and a successful probe also reads an index block followed by a data block. So a single lookup can trigger many I/O operations. If you have 10 level 0 files and the key didn't exist, you still touch all 10 Bloom filters. On a spinning disk, that's 10 seeks. Even on an SSD, it adds up. When combined with deeper levels, a single point lookup might hit 15 disk reads. That's the hidden cost. To be more precise, the read amplification without Bloom filters is roughly the number of SSTables you have to touch. With a typical 7-level LSM and 10x size factor, worst case could be 100 reads. A Bloom filter slashes that to about 1 false positive per level, but level 0 still needs to check every file, so you go from 100 to maybe 10-15 reads, still an order of magnitude more than a B tree's typical 3 to 4 reads. In a large write-heavy deployment, after a sudden write burst, level 0 ballooned to over 40 files. P99 read a latency jumped from less than 5 milliseconds to more than 30. The reads, normally hitting just a few files, now had to probe over 40 Bloom filters and then dozens of index blocks. This is the real consequence of uncontrolled write spikes in an LSM. Compaction is the main mitigation. It takes overlapping level 0 files, merges them into a single sorted level 1 table, removing old versions. But compaction isn't free. It consumes disk, I/O, and CPU. If you're not careful, fierce compactions can compete with your reads, making latency even more unpredictable. This is the classic LSM trade-off. You trade steady-state read cost for write throughput, and eventually pay for compaction. I once debugged a service that was suddenly hitting 200 millisecond reads. The team had set the compaction trigger too high. Level 0 was allowed 32 files. During traffic bursts, compaction couldn't keep up, so each read had to touch over 30 Bloom filters and index lookups. The fix was to reduce the level 0 compaction trigger to 4 files and increase compaction threads. Latency dropped back to single-digit milliseconds. In real systems, you add a block cache for Bloom filters and index blocks. A hotkey might have its Bloom filter pinned in memory, removing 1 disk I/O. But the structure still forces sequential probing of level 0 files, and if your working set doesn't fit in the cache, reads become I/O bound fast. A more advanced technique is partitioning level 0 key ranges. RocksDB's partitioned filters store 1 Bloom filter per block, not 1 for the entire SSTable. Instead of loading a multi-megabyte filter to check a key, you only load the filter of the block where the key would reside. If the key is missing, you often need just a single small disk read, a few kilobytes instead of a few megabytes. This dramatically reduces I/O for point lookups, but random write patterns can still scatter data across many blocks, forcing multiple filter reads. So when does all this pain make sense? LSM-trees shine when your workload is write-heavy and you can tolerate moderate read latencies. Think time series data, logging, message queues, or secondary indexes where the data volume is huge and you rarely need sub-millisecond point reads. If your system does 90% writes and 10% reads, an LSM is almost certainly the right choice. The sequential write pattern also gives great space efficiency and low write amplification, which is critical on SSDs. On the other hand, if you have a read-mostly workload with strict latency SLAs, like a user-facing key-value store where every lookup must be under 1 millisecond, a B tree is usually better. InnoDB or WiredTiger keep a balanced tree with a large buffer pool, so many reads hit memory directly. The cost of a B tree write is higher, but reads are consistent and low. I've seen teams choose RocksDB for a metadata store with 80% reads and 20% writes, and they kept chasing red tail latency until they switched to a B tree. In raw numbers, a well-tuned LSM might give you 100,000 writes per second and 10,000 reads, while a B tree gives 20,000 writes and 50,000 reads on the same hardware. The write amplification on a B tree is 3 to 5 times higher due to page splits and random writes, while an LSM keeps write amplification low by only rewriting data during compaction. There's no magic, it's a physical consequence of the data layout. So to wrap up, LSM-Trees trade disk reads for fast writes. The log structure design forces every read to traverse multiple files, causing read amplification that spikes when compaction lags. Bloom filters are essential, but they only reduce the pain, not cure it. Compaction is the background hero that keeps reads manageable, yet it consumes resources and can itself starve reads. Know your workload. Write heavy and huge, go LSM. Read latency sensitive and small, stick with a B tree. The hidden cost is real, but understanding it lets you design systems that actually deliver on the promise. Thanks for watching. I hope this one was useful. See you in the next video.